Greetings from Academic Catalyst. I'm Anu Rangan. Today we'll be talking about frost circles. Now, frost circles are very useful in identifying if a given organic compound is aromatic, non aromatic, or anti aromatic. And this is all based on the molecular orbitals. And to just have a fundamental understanding of molecular orbitals, if you have a bonding molecular orbital, that will be the lowest energy and it's going to be the most stable. And that's when we say very likely that it can be an aromatic compound. The non bonding molecular orbital will be slightly higher in energy, so it'll be less stable than the bonding molecular orbitals. And when we get to the anti bonding orbitals, which will be the highest in energy and they'll be least stable, and generally the anti aromatic compounds fall into this category. When we are drawing the frost circles, there are certain small little things that will help in analyzing how to draw them. So let's say, for example, we are starting with benzene as the example here. And we know that benzene has 6 carbons in a ring, and there are 3 double bonds accounting for 6 pi electrons. So before we start drawing this circle, we want to just draw the polygon shape first. So you draw the polygon, which is hexagon in this case, and then you can draw a circle around it. So when you draw the polygon also, you want to ensure that one of the vertices of the polygon is in the center bottom of that circle. So this is what is you want to be very comfortable drawing the center here, and then you can start drawing the other. So basically, if I were to have something like this, I would have 1 point here, and then I can see that there are 6 points on the hexagon. So then from here, I'll draw 2 more on this side, 2 more on the next one, and 1 at the top. And then you can connect them, all of it that way, if that works. Either way, you want to make sure that you have a circle and the polygon inside such that one of the vertices is at the bottom of that circle. So once you have drawn the circle and the polygon, you can draw a line which is going at the center of the circle. That's like the horizontal line here that divides the polygon into 2 halves. So this is going to be the non-bonding orbital line. So if you see here, we have a non-bonding orbital line in the center, and then anything above that will represent the anti-bonding molecular orbitals. Anything below that will be the bonding molecular orbital. So in this case, we have had 6 vertices on the circle, each of them representing a molecular orbital. So we have the bottommost one, and then we have 2 in the same energy level above that, all 3 of them constituting the bonding molecular orbital. And you can see that there are no vertices along the non-bonding, so there's nothing from the polygon touching the circle at this level, so there is no non-bonding molecular orbital here. And then we can see that there are 2 anti-bonding molecular orbitals of the same energy right here and here, and 1 at the highest energy in the antibonding molecular orbital. So once you have drawn the circle, once you have drawn the polygon inside it and have identified all the vertices that are touching the circle, and then you have identified the non-bonding and the bonding and antibonding, that's when we start filling in the electrons. Now, as I said, benzene has 6 pi electrons, and we start filling these molecular orbitals with those electrons. You start with the lowest energy, that's going to be the bottommost here, and then we have 2 energy levels at the same level, so you will first fill them individually, and only if you have more electrons, you start filling them to complete the pairing. So in general, if you were to draw something here, so let's say we are drawing. So we have identified that this is the non-bonding molecular orbital. We have anti-bonding 2 of them, 1 on the same level and 1 at the higher level. And then we have 2 bonding and 1 lowest energy right there. So what I do is I start filling in put the 2 electrons here at the bottommost because we have 6, so that gets filled first. And then I'll place 1 electron in each of the orbitals which are at the same energy level. Only if I have more electrons, I start pairing. So in this case, we have only accounted for 4. There were 2 more left. So I can pair 1 here, pair the other one here. And then I'm done with all the 6 electrons. So you can see that all the electrons in the bonding orbitals are all paired bonding orbital. So that means the molecule is going to be very stable and it's going to be aromatic. Now let's take another example, which is cyclobutadiene, and it has 4 pi electrons. So we draw the circle such that one of the vertex is at the bottom of the circle, which means the 2 other will be in the middle and there's 1 at the top. So now the 2 middle ones are right in the non-bonding. So this will be my non-bonding orbital, molecular orbital. And we have 1 anti-bonding molecular orbital and 1 bonding molecular orbital. So if I were to draw the structure and fill in the electrons, we start with the bottommost, we fill it with 2 electrons here, and we have 2 more, which means each of these equal energy orbitals will get 1 electron. So that means you have an unpaired electron in the non-bonding orbital here. So whenever you have unpaired electrons, that means it's going to be anti-aromatic. So unpaired here. So this will be anti-aromatic. Unpaired electrons are always the least stable. They're highly reactive. Think of the radicals. Radicals have an unpaired electron, so they're extremely reactive. The more reactive or more unstable the molecule is, that means it's lower in stability. Now the frost circles, we can take a few more examples. If you were to look at a 3-membered ring right now, so there are 3 options here for a 3-membered ring. We have 1 double bond and there is no charge on the third one. We have 1 double bond with a positive charge on the third carbon, 1 double bond and a negative charge on the third carbon. So if you look at the number of electrons, the pi electrons is what we are looking at. So we see that there are 2 pi electrons in the first one and 2 more pi electrons in the second one, the positive charge indicating that there are no electrons. It's an empty p orbital. And then we have the third one with 2 electrons here and another 2 electrons in the negative charge, making it 4 on that one. Now the first one will be non-aromatic, mainly because there is no p orbital on that one. This is an sp3 hybridized carbon, which means there is no conjugated pi bond. So the 2 electrons in the p orbital will be right here. They cannot move into the orbital on the third carbon. So in these cases, we do not have to draw the frost circle because it's automatically non-aromatic because it doesn't have p orbital on all the atoms in the ring structure. Now the second one, the very fact that we have a p orbital, the carbocation here, that means there is an empty p orbital here. So empty p orbital, that means these are also p orbitals here with the pi bond. So these 2 electrons can actually move from the 2 carbons here to these 2 carbons and from there to the other one here. So they can go through the entire ring. So it becomes conjugated. So now once we have the 2 pi electrons here, we draw the circle and we put the 3-membered ring such that one of the vertices is at the bottom. And then we have identified that there is 1 bonding orbital here and 2 anti-bonding orbitals. So when we start filling in, we have 2 electrons, we fill it at the bottommost. And so once it is done, you can see that it's a paired one at the bonding orbital, so it becomes aromatic. Now in comparison, if you look at the last one here, it has 4 pi electrons. We have the same ring and the 3-membered organic compound inside that. And you can start to fill the electrons. We have 2 electrons in here, and this is going to be the bonding, and then we have unpaired electrons in the antibonding orbital, so it will be anti-aromatic because of the unpaired electron, especially so in the antibonding orbital. Now if you were to extend this for a 5-membered ring, so again we are only using the samples where it is conjugated within the ring. So here this is an empty p orbital with a positive sign. This is a filled p orbital, so which means it will have 2 electrons in that. So that's the reason we have 4 pi electrons in the left one and 6 pi electrons in the right one. We draw the Frost circle and put the pentagon inside that such that the vertex is at the bottom here. And you can see that we have 1 lowest energy, 2 above that, and 2 more in the antibonding. So all these 3 are going to be in the bonding region, and this is the antibonding region. There is no non-bonding here because at the center, nothing touches the circle. So if you have the 4 pi electrons, we start filling in, and we can see that there are 2 in here and 1 unpaired in each of the next level. So that's why it becomes anti-aromatic. On the other hand, if you see the one on the right, we have 6 electrons, so we have 1 paired at the bottom, and then we can have paired ones even in the next level. That's the reason it becomes aromatic. Finally, we'll look at heteroatoms here in the ring, where the nitrogen and oxygen. And nitrogen, whenever you have a single bonded nitrogen, when nitrogen is single bonded, it has 1 lone pair, you can consider this to be in the p orbital. However, when the nitrogen is going to be in a double bonded structure, when you have nitrogen in the double bonded structure here, so you will not consider the lone pair, but you already have pi electrons. Those will be in the p orbital. So you will not consider these lone pairs for this case, but you will consider the double bond. But if it is single bonded, you will consider the lone pair as being in the p orbital. So we have the left one, which is pyrrole. Pyrrole is a molecule which is a 5-membered ring with nitrogen as one of the members. And it has 2 double bonds that are conjugated, and then we have a lone pair of the nitrogen. Now because this nitrogen is single bonded, so that means these 2 lone pairs will be in the p orbital because there is an sp2. This is sp2 hybridized, this is sp2. And this will also be sp2, making these electrons in the p orbital electrons. So which is the reason why we consider this ring to have 6 pi electrons. Now we draw the circle and we have the apex at the bottom of the circle. The pentagon is placed such that one of the vertices is at the bottom here. And then we have 1 level here, 2 levels here, 2 more levels here. So we have 6 electrons. We start filling in 2 in here, 2 in here, and 2 in here. So all 6 are paired, so this becomes aromatic. Now in case of furan, which is oxygen, oxygen has 2 lone pairs. You will only consider one of them in the p orbital. The other one will be in the sp2 hybrid orbital. So only 1 pair is going to be considered. The other one should not be counted towards the pi electrons. So this also has 6 pi electrons, which is why we'll end up with paired ones in each of those orbitals, making furan also aromatic. So this should give you an idea as to how to identify if the molecule is aromatic or anti-aromatic using the Frost circles. So just to summarize, finally, being comfortable drawing these polygons within the circle is going to be very useful. So maybe you can try out drawing these structures and ensure that each of them has a vertex at the bottom of that here. You can see that this is the most important thing that we need to ensure in the Frost circle drawing. Thank you for listening. You can feel free to get to the web page if you have any more questions, or follow these videos for any more topics. Good luck.